All right, I hope it is now. So we have here a rod which is on a frictionless pin here, okay, and that is friction. Okay, so we can start rotating it. Give it a little push, it will rotate. So there's some friction or it will stop depending on how much force you initially gave. So we can make it rotate. Let me bring it back to that position. What I'm trying to do now is to introduce a concept called torque. Torque is from a force, okay? Without a force, there is no torque. A force will have. Torque is a term that we use to give the tendency of rotation that is given by a force, right? In rotation, we need another concept called torque. Force is not enough. Torque is the tendency of a force to make something rotate. Now I can show you it depends on not only on the magnitude of the force and some other factors as well. It is, I'll apply a force, I will show my force that is applied. Right, so this is, I'm showing the force. The force is applied at the edge of that. This is where it is going to rotate. Now it is not yet applied. When I push this button, it will be applied for a short period of time. It will be not constantly. And because of the application of that force, it will start spinning. So it is coming and say it will stop because of friction. It is not a constant application of the force, it's only impulsively. So I can see that, you know, the angular velocity it gets, it is accelerating from 0 to some angular velocity, but it get, because of friction, it stops and say it stops here. So we can have an idea, rough idea, how much angular velocity it was given initially, depending on how much it rotates, the angle. Let me bring it back and bring the force. The amount, the force is 9 Newton. It is applied an angle of 90 degrees to the force. Fine. So the tendency of turning from this force, we have a name, it's called the torque, and we also give a symbol for that, this Greek letter tau. It's not T, it's a Greek letter again, it is called tau. This is how it is written. It looks like a T, but it's not quite. It's called the Greek letter tau. So this is the symbol we use for torque. You can see if we increase the force, it is going to have a bigger angular acceleration. It will come out with a great angular velocity. So this torque is obviously proportional to the force. More force means more torque. Understood? There is no problem with that. I can show you, I can increase the force, but I will skip that. So you're going to believe me, yes, because it's easy to see. Right, now I'm going to do something different. I'll bring it halfway here. So the force was initially applied, at the end, now half the distance from the pivot point. So this R, the distance from the pivot point where the force is applied now become less. What do you think? The turning will be less, right? It will be less. So the turning effect depends not only on the force, it also depends on this R. Now you will accept with, you will not have difficulty accepting what I said. We can even show it. Let me push it and see. Before it stopped here, now it is going to stop somewhere halfway between that and this. Actually, it's proportional. It is proportional to R. We can simply write this. The torque is equal to distance to the application of the force multiplied by the force. So we even have a name for that. We call it torque, and the symbol we use is this Greek letter tau. And what about the unit? This is Newton, this is meter, the unit will be Newton meter. So we have a name for it, it is called the torque. So torque, when you apply a force like that, it depends not only on the force for the rotation effect, it also depends on the distance to the application of the force from the pivot point. That's very clear. Let me do something different now. Okay. Now I'm going to apply it in the same place at the end, upward. But this time, this is 9 Newton. I'm going to apply at an angle. Keeping this red arrow is the force. These are the component of the force. We show the two components. One is long parallel to the rod, the R direction, and one perpendicular to the rod, the purple one. Green is the parallel component. We can show it like this, F parallel, and this is the perpendicular component, perpendicular to the R along the rod, parallel to the rod. I'm making sure this is still 9 Newton. It is 10.5, it is more, so I have to reduce it to 9 Newton. We use the mouse here. Yeah, 9 Newton, right? So the length is the same as when I had here, but I applying at an angle of 30 degrees or whatever this angle. It is not 90 degrees now. So what happens to the purple arrow? The perpendicular component is not 9. The perpendicular component is now less than 9. Before it was 9. So what do you expect the effect? It came all the way here, right? Would it come all the way here? The angular velocity will be less. So that is what I'm trying to convince you about. It is still 9 Newton. The total force is still 9 Newton, but the perpendicular component is less than 9. You can even see it here. The perpendicular component is 4.89 because it is applied at an angle. So what you realize now is not just the force, it is actually torque is equal to R multiplied by the perpendicular component. So this is the correct equation. If it is perpendicularly applied, then perpendicular component is the same as the total force, so no problem. But in general, this is the correct equation. Torque is equal to distance to where the force is applied from the pivot point multiplied by the perpendicular component of the force.
So if I made the angle more than 90.
Yeah, that's, you cannot make it more than 90, right? How can you make it more than 90, right? No matter how much you turn, it is either maximum is 90 or minus 90, okay? So, all right. So, it is very nice. I mean, you are asking the right questions. This perpendicular component is F sine theta. Theta, when you say more than 90, yes, you are right. You can make theta more than 90. What it means is, you are here, right? Your question is valid. This is 90. This is more than 90. Yeah. But the more than 90 is the same as, sine 90 is the maximum. Sine 100 become the same as sine other side, which is sine 80. Sine 80 and sine 100 is the same, right? It is less. Okay. So for the sine, it is symmetric about the vertical line. Okay, so it doesn't matter whether it is something less than 10 from 100, 90 or more than 10 from 90, it is the same value. Good. I mean, your question is valid. I cannot say you cannot make it more than 90. So this is the meaning of making it more than 90. Yeah.
Sorry for the interruption, but I have a question about the formula sheet.
Please, when I'm no. How can you finish? Please close your laptop. You don't have it in your laptop. Please close your laptop, please. Now, close it now. Down, down. I don't want you to look at the screen. Please close the laptop. It's okay. I want to see it closed. Thank you. No. We will finish the lectures, okay? So, right. So, the torque is equal to R distance to the application of the force multiplied by the perpendicular component of the force. Now, another thing I need to tell you, that torque is a vector. It has direction as well. So, let me. Okay. So, you are applying it here. Which direction will it turn? The pivot point is here. If I apply the force, whether it will go counterclockwise or clockwise? Counterclockwise, right? So that is positive direction. Counterclockwise is positive direction. Let me say, if I put it here, which direction will it turn? Counterclockwise or clockwise? Will it turn at all? What is R equal to? R equal to 0. The torque will be 0. Because the distance to the application point is 0. From the pivot point and the application point is the same place. R is equal to 0. There will be no torque at all. So it will not turn. It's 0, there is no direction. Let me bring it to this side. Now which direction will it turn? Clockwise. So torque has direction. Like the angular velocity has direction. Also it's one dimension. We have only two directions, positive direction and negative direction. Okay. So let me now go to the slide. So this is your chapter 8. The title of this is Rotational Equilibrium and Dynamics. So we will be covering these topics. I have already introduced this talk, okay, but we will do that here also. Now you understand better because you looked at the simulation. Then the second topic will be center of mass, center of gravity, the same thing. Third topic will be equilibrium condition. Now we will have a very general definition of equilibrium condition. Then number 4, we will bring in the Newton's second law, how to apply in rotational motion, the dynamics of rotation. The 5 and 6 are omitted because we need time for final exam, so we will not cover that. Okay, let me clear this mess. So you see the application force is important where in a rigid object and rotational motion, where the force is applied is an important factor. We cannot neglect it. We cannot say it's all point object. No, not anymore. We are bringing in rotation. The concept of rotational equilibrium, that is the second thing that we'll come to. Then angular momentum, we will not have time to do that. So these are skipped. Force causes acceleration. We know that. Newton's second law, net force is equal to mass into acceleration. Torque is something, not something coming from nowhere. It is coming from the forces. For every force, there will be a torque. We discussed that. Torque causes angular acceleration. So that's the difference, okay? When you are talking about rotational motion, what is important is to consider the torque, not just the force. And of course, they are related. We already saw the equation, but we will go through that again. Now, if you look at this is a door, you are looking at a door, and the door is hinged at a point. This is where it is going to rotate. And knob is there. You use the knob to turn it, right? So you open the door. Why don't you put the knob here? It's ridiculous, right? You need to use a big force because turning the door, opening the door means rotating the door. So R bigger mean the tendency of the force to rotate will be bigger. So that's why we keep the knob as far away from the rotation axis. So understood. So this is a very practical application of what we are learning. So this torque, or the tendency of the effectiveness of the force in opening the door depends on the magnitude. We saw that more magnitude, it will be open faster. So it will, rotational velocity will be greater than the initial. Position of application of the force, where you apply, is another factor. The angle at which the force is applied. What if you try to open the door like this? Will it ever open? No, right? Why? There is no perpendicular component. Perpendicular component is 0. F sine theta. Theta is equal to 0 means sine 0 is 0. F sine theta is 0. So nothing. We need a perpendicular component. Without the perpendicular component, it is not going to turn. Right. So we started by saying this, then we understood, okay, then this is the unit, then we understood what is important is the perpendicular force, right? So we can demonstrate it by, again, we went through this, but this is a very nice practical example. We have, this is called the wrench. Now what it is, by looking at the picture, you use this to open this nut, right? So you apply the force here. If you take your hand and put it like that, is it a good idea to do that? Is what it means, R is very small. So the turning effectiveness will be, the torque will be, it's the same force. You're applying, say, 100 Newton, you apply 100 Newton and 100 Newton. What is the best way to turn? To make it as far away from the rotation axis, the turning effectiveness will be greater. So it's very clear. So it's a nice application of what we learned. Right. And direction, we talked about it before also. What is the direction of this torque? Torque also has direction. In which direction it is trying to turn, that is the direction of the torque. So it is counterclockwise direction. So counterclockwise positive, clockwise is negative. So you should keep that in mind. Here you see the same force is applied, right? But this will have the greater torque, the last one. Torque is a vector quantity. Okay, they have direction. So the clockwise will be taken as into the board direction, and counterclockwise will be taken as the right-hand rule for the angular velocity. So if it is rotating counterclockwise, you have to keep your right hand so that you can curl your fingers. If you keep like this, you are going to curl counterclockwise, right? So you have to only keep like this, so you can curl your fingers. If you keep like this, you are curling clockwise. So you have to keep like this to in the same direction as the direction of the turning effect, which is counterclockwise, and thumb is pointing outward. So outward is the positive direction, which corresponds to counterclockwise. So torque is a vector quantity, and the direction will be perpendicular to the plane, either out of the plane or into the plane. So when it is clockwise turning, the torque will be negative. When it is counterclockwise turning, the torque will be positive. But now, the angle is not always 90 degrees, right, when you apply the force. So what is important is the perpendicular component of the force. So that can be demonstrated again with the same wrench. So if you apply the force not at 90 degrees, but set an angle of 30 degrees to this R, what happens? The turning effectiveness will be less. But at 90 degree, it will be the maximum. So in other words, what is important is the perpendicular component of the force. So for example, if you do like that, what is the perpendicular component? 0, right? But if you increase the angle, the perpendicular component is f sine theta. As theta increases, sine theta will increase, and it will come to maximum when theta is equal to 90. When it is more than 90, again it will be reducing. You know the graph of sine theta versus theta. So it goes like this, right? At 90 degrees, it is maximum. Then after more than 90 degrees, it reduces. So that's okay. So putting it all together, you can say the torque, the general equation is this. It is not R into just F, but the perpendicular component of F. So the sign we use for perpendicular component, this means perpendicular in math. Okay. So when you put this sign, so F subscript this means perpendicular component, and no perpendicular component is F sine theta, where theta is the angle the force makes with the R or the rod. Okay, that's very clear. Now we come to something, another interesting way of looking at it. So again, we are looking at the door and we are applying a force which is at an angle theta. So generally you will say, okay, torque is equal to R multiplied by not F, but F perpendicular. So therefore R F sine theta, because F perpendicular is equal to F sine theta, we are happy. Right, now I want to suggest to something else. What I will do now, I'll take this force and I will look for the distance of this force, the perpendicular distance of this force to the rotation axis. So to find that, I will extend the line of action of this force, and I can see this is the perpendicular distance of the force to the pivot point. This is the perpendicular distance, so I am going to call it perpendicular distance. And if you know your trigonometry, if this is the angle theta, this will also be theta, then you can see that for this right angle triangle, sine theta is equal to opposite divided by hypotenuse. Opposite is equal to R perpendicular, hypotenuse is equal to R. Therefore, R perpendicular is equal to R sine theta. I am proving that. R perpendicular, the perpendicular distance of the force to the pivot point is equal to some. You are coming and you are leaving. So I can also say the torque is equal to the total force, not the perpendicular force, multiplied by the, instead of the R perpendicular. Why is this correct? Because you can see that R perpendicular, I proved it to be R sine theta multiplied by F, so you get exactly the same answer. So I am proving I can find the torque in this manner as well. This R perpendicular has a name we call the lever arm. So you can say we can calculate the magnitude of the torque by alternatively by this equation. I get the total force, not the perpendicular component, multiply by, if I know the perpendicular distance of the force to the pivot point. Why is it keep changing? Oops. Yeah, we are here, right? Yeah. Right. So that is another way of getting the magnitude of the torque. So I can write it like that. Torque, you can get it from this, good, or you can get it from this. They are both correct. Actually, both are equal to R F sine theta. So you can just, if you know the R, substitute for that. If you know the magnitude of F, substitute for that. And if you know the theta, substitute that. That will give you the torque, the magnitude of the torque. But you know the direction, you should know how to get it by looking at whether it is trying to rotate it clockwise, that means negative. If it is trying to rotate it counterclockwise, then it is positive. But the magnitude is simply use that. Right. So the right hand rule, I mean, counterclockwise is positive. So you look at it and see which direction it is trying to rotate it. Now, here the wrench is giving a force to the right, and which direction is trying to rotate it? Counterclockwise. clockwise. So it's a positive torque. It's very clear. That is the easiest way. The right hand rule means you take your right hand and put your finger in the direction of R. R has a direction. It is from the pivot point or the axis of rotation to where the force is applied. So, and see whether you can curl your finger in the direction of the force. If you keep it like this, can you curl your finger in the direction of the force? No, it's in another direction. So you have to keep it so it faces the force. Then look at the thumb. Thumb is pointing out. So that is the direction of the vector for the torque. Well, counterclockwise out of the board. Clockwise into the board. Right. You can have more than one force acting on an object. That means each force has a torque. That means we can have more than one torque acting on an object, two or more torques. Then you need to add them, right? If you have more than one torque, to get the net torque, you have to add them. You can simply add that, but you know, they are vectors, they have direction, but here it's only two direction, positive direction and negative direction. So you algebraic addition, take care of the sign, that's it. You don't have to worry too much about it. Sometimes the net torque can be 0 because one torque is say positive 10, the other torque may be negative 10. When you add, the total net torque will be 0. So the value of the torque depends on the chosen axis of rotation. Let me explain what we mean by that. Let's say we have a rod lying there and you apply a force. Let's say you apply a force like this, say F is equal to 10 Newton, and say there's a point A here. The distance to point A, let me say RA is equal to 1 meter, and says there's a point B here. The distance to point B, let's say 2 meters. Now if someone asks you what is the torque, just like that, do you have an answer to that question? Really not. Because you have to tell me, okay, you ask him for me for the torque, talk about the point A or talk about the point B. For this particular force 10 Newton, let's say F, find the torque about the point A, that will be one answer. Find the torque about the point B, that will be another answer. So that you have to keep that in mind, okay? So whenever someone asks you for the torque, you have to tell me, all right, I'll find the torque of this force, but tell me about which point. The question is not complete without telling about which point it is. So that's the point here. So for example, torque about A will be 10 Newton multiplied by 1. Because the distance to the point A is 1. But torque about the B will be 10 multiplied by 2. Okay, it's clockwise, right? Both of them are clockwise because trying to, so it will be negative, negative. If it is making 90 degrees, sine 90 is 1, so it's both of them. So this is very important, okay? You may be, the real physical rotation may be about A, but still I can ask to give me the torque about point B. That point doesn't have to be the actual physical rotation point. It can be any point, okay? So it doesn't have to be the physical rotation axis that is present. You can take the torque about any point we want. So now we come to the second concept, the center of gravity concept. The same as the center of mass, okay? Because as long as we have the same gravitational acceleration, correct explanation, we know it's a constant, okay? If you are not changing the height too much for a object of any size, you know, it is going to be the same value everywhere. In that case, center of gravity and center of mass is the same. Now, what we mean by center of gravity? There are some nice like tricks and all, you know, click on these links and please watch those videos. And about the center of gravity point. So what we mean by this center of gravity point? let's say we have an object like this, okay, say irregularly shaped. The center of gravity points, I can say, is the point where the whole gravitational force is applied. Okay, so let me say this is the mg is the gravitational force, right? Mass, total mass multiplied by the gravitational acceleration is the gravitational force. Actually, every point, if you take the point m1, small mass of m1, the gravitational force for that particular point mass will be at this point. Then on the mass m2, the gravitational force will be at that point, and so on. So can we define a single point where we can imagine the total gravitation, the weight of the whole thing is applied? That particular point is called the center of gravity point. So we have a way of finding the center of gravity point. If it's a symmetric object, it is easy. You can say it is the center, geometric center. But it's a regularly shaped object. It's not that easy. But we have a ways of getting a formula for the center of gravity. It's as follows. We break it to small pieces and find the coordinate of each piece. So say m1 is x1, y1, m2 is x2, y2, m3 is x3, y3, and so on. And we say, okay, this is the point where the whole mass is concentrated, so rather the whole weight is concentrated. And let's say this is xcg and ycg. Then we will say the turning effect from individual force and add them is equal to the turning effect that comes from the total weight at the center when it is acting at the center of gravity point. So this is the equation that we will use to find the center of gravity coordinate. So we can take the torque from each one of them. So for the m1g will be m1g into x1. If we take the y-axis as the rotation axis, so for this particular m1g, its distance to the y-axis will be x1. So the torque from this guy will be m1g x1. Torque from the second mass, say m2g, will be its x coordinate m2g2, m2g x2, and add them all, and we'll say it is equal to the torque from the entire mass concentrated at the center of gravity point. We wish to locate the point of application of a single force, so properly worded here, whose magnitude is equal to the weight of the object and whose effect on the rotation is the same as all the individual particles. This particular point is called the center of gravity of the object. So mathematically, we can write it like this. This is the sum of all the torques from individual particle, and this is the effect due to the single point where we think all the weight is concentrated multiplied by its turning effect around the y-axis. So it will be x center of gravity. So G will cancel on both sides. Then if we take it to the other side, that will be the total mass. So you get this equation for the x center of gravity. Similarly, if we consider the turning effect around the x-axis, we will get the y center of gravity like that. And of course, if we consider all three dimensions for the z center of gravity, we'll get that one. So if you understand this equation, you can see that x center of gravity is equal to, what do you mean by sigma my xi? It means, suppose you break it into three particles, it will be m1 x1 plus m2 x2 plus m3 x3 and other particles and so on, divide by the total mass m1 plus m2 plus m3 and so on. So that's the equation for the center of gravity. Now we say this is same as the equation for center of mass, so there's no difference between center of mass equation and the center of gravity equation as long as G goes away, can get cancelled. So this is the second equation that we learn, the center of gravity or the center of mass equation. Right. Can we find the center of gravity quickly? We can do it for if the object has some symmetry and if it is a homogeneous object. What do you mean by homogeneous? The density of the object is everywhere the same. Okay, that is the meaning of homogeneous object. Provided it is also a symmetric object, then we can, please pay attention here, please. Close your laptop. You can look at my screen here. Let me take a square. And let's say it's a square sheet and it's made of the same material, homogeneous. Everywhere it's the same density. And center of gravity will be at the geometric center. So it must be lying on its symmetry axis. The center of gravity must be on the symmetric axis. Okay, so let's say I take the green. If I draw a line like this, it's a symmetry axis, right? It is equal either side of it. That's a symmetry axis. So I know the center of gravity must be on this green line, somewhere on the green line. I can draw another symmetry axis. This is also a symmetry axis. Now someone can say, no, the center of gravity is on the red line. Both should be correct. So what is the only point that satisfies both requirements? The intersection. So then the center of gravity is here. It is lying on the red line, which is a symmetry axis. It is lying on the green line. It is also symmetry axis. So that's very easy to find the center of gravity when the object is homogeneous and there is some symmetry. All you have to do is draw two symmetry lines. The intersection of the two symmetry lines is where the center of gravity is. All right. What if the object is not symmetric, like this guy, not homogeneous, not symmetric? Experimentally we can do something. We know the center of gravity must be where the center of gravity is. Okay, let me explain what I said. Say the wrench is a regularly shaped object. There is no symmetry at all, and it's not a homogeneous. It may be, maybe this part consists of some other material. It may not be homogeneous. All you do is the following: take a rope and choose a point in this. Say let's say point A, and connect a rope and hang it. And we know because of the gravity, it will align the thing and it will come to certain balance. Then we know the center of gravity must be on this line. If it is not in the line, the gravity will apply a torque and it will come and bring eventually, it will align in such a way. So when it is balanced, the center of gravity must be on this red line. We know for sure because of the balancing. So you take a red pen and draw this. The line AB. We know the center of gravity must be on the red line after it is balanced. All right. Then you cut it and connect it to another point, any point, doesn't matter which point it is. Let's say I choose the point C, say black. Okay, let's C. Let me say I choose this point C. And I tie a rope and again make it balance, hang it. Now I know it must be on this. The red line is already there from my previous experiment, so I mark it. I know it is on the red line. Okay, the center of gravity must be on the red line. Now I conclude it must also be on this black line. Right. Again, the same story. The center of gravity must be on the red line. Now I know it must be on the black line. How can I satisfy both? The intersection. Intersection of the two lines is a point which satisfies both conditions. So I found the center of gravity. Where they cross is where the center of gravity is. Okay. So we are talking about the torque again. So we stopped it and coming back to the torque. We finished the central gravity thing. We need to sometimes find the net torque, because when we want to apply the Newton's second law now, the dynamics. Remember what is Newton's second law? Net force is equal to mass into acceleration. So there we wanted to find the net force. Force is a vector and you know how to add them as a vector. Similarly, when you want to do the dynamics for rotation, we need to find the net torque. Okay. So what do you do? I mean, now this is easy because of one dimensional. The rotation about a fixed axis is one dimension, only two directions, positive direction and negative direction. So you know how to add them. You don't need to XY component, we don't need to, because we don't go to this two dimension. It's a fixed axis rotation. We only have two direction, positive and the negative direction. So remember to account for the direction. Whenever it is counterclockwise torque, you put positive sign. Whenever it is clockwise torque, you put negative sign. Don't forget that. Right, now we come to this equilibrium again. We know what is equilibrium. If someone asks you what is equilibrium, it doesn't mean velocity is zero, no. Equilibrium means acceleration is zero. That is the condition for equilibrium. Acceleration is zero. In other words, net force has to be zero. Whenever you have the net force is zero, we can say that is what we learned before. Equilibrium means net force is zero, that will make the acceleration zero, so the velocity will not change. As long as the velocity is not changing, it doesn't have to be zero velocity, it can be any velocity. A constant velocity means it's in equilibrium. Okay, that we call the translational equilibrium. Now we know better. Let me explain this. Take a rod, keep it on the table, let's say the smooth table, and you apply forces. You apply a force of 10 Newton and you tell your friend apply a 10 Newton in the opposite direction. So he will come and apply also 10 force in the opposite direction. Are you in equilibrium now? With the velocity change?
Yes.
Change? Yes. Okay, take this, you apply two forces in the opposite direction. It will not change, right? It is in equilibrium. Net force is zero. Plus 10, plus minus 10, 0. Okay, now. Okay, you apply the force again, 10 Newton, and you tell your friend to apply the force. Okay, he comes, the red guy, he comes and apply it. Is the net force 0 now? Why not? Plus 10, minus 10, 0. Net force is 0. But is it in equilibrium? Try. You apply like this, is in equilibrium. You apply like this. Thank you. It's not in equilibrium, right? This one, net force is 0. This one is also net force is 0. But this one is in equilibrium, that one is not in equilibrium. There is something, this condition is not enough. We need to have this also. Both of them has to be satisfied. Net force is 0. What about net torque? Take a point, let's say we take the middle point. What is the torque from the blue guy? It's clockwise, right? Because this is the R, this is the pivot point, so it is trying to rotate in clockwise. So from this blue guy will be minus 10, let's say it's 1 meter, 10 multiplied by 1 is the magnitude of the torque, and it's trying to rotate it clockwise, so minus 10. But that is not the only torque, there is another torque. From the red guy, what is the torque? 10, again 10 multiplied by 1, 10. But it is trying to rotate it about this point counterclockwise, so plus 10. Plus 10 minus 10 equal to 0. Net torque is 0. Take any point. any point on this rod or even outside, the net torque due to these two forces will be 0. So this guy is satisfying both conditions. Net force is 0 as well as net torque is 0. So it is complete equilibrium. But this guy, he's going to spin about somewhere in the middle. It is going to spin. Let's take, say, this point A. Say, let's say it's 1 meter and this is also 1 meter. Let me use different colors so it's clear. This is the distance for R1. For this guy is applied here. So this is the R2. So now if I calculate the torque, use black, the net torque is equal to torque, let's say this is number 1, this is number 2. Torque 1 is what direction? This is the pivot point, it is clockwise, good, minus 10. Okay, let me use blue for that, so it's clear. Okay, from the red guy, also it is trying to, by this point, it is trying to rotate clockwise. That is also minus 10. Minus 10 minus 10 is minus 20. They don't cancel each other. They reinforce, they're in the same direction. So here the net torque is 0, also the net force is 0. The other side, this guy, net torque is not 0. Both of them are rotating it in the same direction. So we have a net torque. Although net force is 0 on the right side diagram, but the net torque is not 0. All right, okay. So this is the pivot point, right? This is the pivot point. So you are applying this force. Okay, let me number 1. Number 1, imagine it is pivoted here. You push like that. Which direction will it turn? Clockwise. Okay, agree? Right. Now we come to this guy. This is again the same pivot point, and you are applying the force here. Which direction will it turn? Clockwise. Both of them are. Okay, so that is we have to be very careful. Okay, you should be able to figure out which direction is the torque, whether it is counterclockwise torque. It depends on the point, the pivot point we are looking at, and where the force is applied. Okay, right. I think I will stop there. Let me take attendance.